Okay, for 12.3, our learning target, at least one of them, is I can use the integral test to determine if a series converges or diverges. Please note this paragraph. Unfortunately, with few exceptions, and those two exceptions are the telescoping series and the geometric series, with few exceptions, it's often impossible to find an explicit formula for the partial sum S sub n. We've talked about that somewhat, and sometimes we even had the formula for the infinite sum like the geometric series, but that's actually exceptionally rare. 99% of the time, when you're going to be looking at series, you just won't be able to find that. And for that matter, look at this last sentence. For such cases, we will use tests that simply tell us whether the series converges or diverges. That's the big focus, honestly, for the next several weeks. The question will not be, what would this series converge to? What value would it be adding up to? Rather, it's enough to just say, do we know if it does in fact have a finite sum? Now later on, we're going to be able to find that even if we won't know exactly what it would converge to, we'd be able to always find error in one way or another to really help us out. So we'll talk a lot more about that down the road. But our first test, as I'd mentioned at the start of class, right before we started the video, the first test, honestly, is the least often used test. But it's important nonetheless. We're going to say if you have a series, notice there are no bounds written on there, but it's certainly implied that we're starting from a first term going up to an infinite sum. Let's say that f of n is that nth term formula. And let f be the function replacing n with x. We talked about that on our very first day. Now, if f is positive valued, that's the first criteria. There are three. And if it's continuous, that is a second criteria. And finally, for the third, decreasing for every number x greater than 1, then if you meet those three conditions, then you can say the following. If the infinite improper integral from 1 to infinity f of x dx converges, so does the series. Of course, they will not converge to the same value. But what we're saying is the behavior of the improper integral will be the same behavior as you have for the series. By way of comparison, if you work out this infinite series, and if you'd say, oh wow, I'm getting divergence, that means that the series, adding up term by term by term, would of course also diverge. So let's get started and do a couple of problems and see the integral test in action. The integral test, they'd say, use the integral test to determine if this harmonic series diverges or converges. Of course, you should know as a statement of fact that the harmonic series diverges, the most famous type of divergent series you'll ever see. And we can just state that as a matter of fact. But if this integral test is really effective, if it's really going to work, it should, in this case, demonstrate divergence of the improper integral. That being said, start off with f of x equals 1 over x. A sub n is 1 over n. That means f of x is 1 over x. There are three things you must state. And if you don't actually give reason to show that you're checking, technically you're not validly using the integral test. You have to state that f is positive. Just look at this. If I'm starting at a first term, in this case x would equal 1, and then I'd go on forever upward, would f be positive? Yes. F of x clearly is greater than 0 for x greater than or equal to 1. You have to make that statement because those three things that we underlined up above are going to come into play. If you're not meeting those conditions, you're not allowed to use the integral test. Second of all, you're going to have to say that f is continuous. Well, yeah, f is continuous. There's only one value that you wouldn't be continuous at. What's that? Right? F is not continuous at x equals 0. But we don't even have to worry about that. It's continuous for x greater than or equal to 1. And here's the third one. F is decreasing. Well, now we're talking about using some calculus. Because the definition of having a function to be said to be decreasing means what? That its derivative is negative. Hey, very famous derivative here. I hope you've got it memorized even. What's the derivative of 1 over x? Negative 1 over x squared. And you'd say, well, wow, you know what? That numerator is negative. That denominator is guaranteed to be non-negative as well. If you're squaring values of x greater than or equal to 1, what did we just see? That means that f is decreasing for x greater than or equal to 1. Well, that now means you can investigate this integral. You can work this thing out. Try to get an answer for that improper integral. If the improper integral will converge, the summation, the addition of that series term by term would converge also. If this improper integral diverges, you get divergence for the series as well. Now, please remember, this is so critical. Whenever you've got an improper integral, what should be your first step? What should you always write out? A limit. AP graders are going to look at this, and as soon as you don't put a limit down, even if you get the right answer, that's not enough. You can see that you won't get full credit. And so improper integrals are going to continue to show up in our course. And now we'll just say, well, now let's work out this integral. What's the antiderivative of 1 over x? ln of x. Do I need absolute value around them? No, because everything is positive here. I'm going from 1 to going very, very large. Let me just continue some work over here just to space some things out. Give a space for number 2. This would be the natural log of t minus the natural log of 1. But what's happening? Natural log of t as t goes to infinity. This thing, what? Goes to infinity. This diverges. That means that this series diverges by the integral test. I need to tell you this too. You're going to see me write by such and such very, very, very often. That's because in this chapter we're generally doing proofs of sorts. Not like the proofs that you did in geometry, but more or less giving a good solid reason for how you know that your series is converging or diverging. So we'd like to reference the test that we are using. And that is very good practice to get into. Okay, are we doing okay? Let's take a look at number 2. And, we can look at number 2 here and say, wow, does this series converge or diverge? We can say here's f of x equals x all over e to the x. And here's my question for you. Do you think f is positive for x greater than or equal to 0? Definitely. Definitely. If you think about that, your numerator, if x is greater than or equal to 1, your numerator is always positive. E raised to a power is always positive. You're checking this out. Do you think we're always going to be continuous? Yeah. Absolutely. F is continuous for x greater than or equal to 1. You don't have to worry about any values of x that would cause f to be undefined. You would see that your limit as x would approach any number would exist, and it would agree with the function value. That would be the official three-pronged test for continuity. I think we can just make a quick statement that we have continuity. Here's something that we do have to talk about, however. Take a look at this derivative. I think it can get kids upset. Kids might say, oh, you're going to need the quotient rule. Yeah, look, you'd say low d high minus high d low over low squared. And let's work this out. We'll have our low function, e to the x, times the derivative of the high function, which is 1, minus x. Well, the derivative of the low function, e to the x here, is just e to the x. And down below, we'd have e to the x squared. And this right here is where kids can get a little bit nervous. They might say, I'm looking at that. Who's to say that that derivative is negative? As you look more closely at it. Because remember, we need to make reference that this function is decreasing. Well, look, you can factor out e to the x from both of these. And this is really e to the 2x, but I'll tell you what, we can do some canceling. You can say an e to the x would cancel e to the 2x and leave just an e to the x left. But now you look at that and you think, well, okay, so it's a little bit nicer looking. Here's the ultimate, quandary that we have to answer. Is that thing really negative? And real quickly, kids will say, hey, I plugged in a 1, Mr. Dobner, it's 0. It's not negative. I say, ooh, good point. And your denominator is always positive, but if x were equal to 2, if x were equal to 3, if x were equal to 4, would you agree that that numerator then would be negative? So look, I'm going to say this is less than negative for x values that actually are going to be greater than or equal to 2. You can worry about what's happening right there, and you can think, oh my gosh, I'm not getting this to work out quite the way I wanted it to. As long as you show that you are eventually decreasing, you're good. Eventual decreasing is fine. So you could technically say, well, my first term didn't have a negative derivative. Yeah, we don't have to worry about that. So instead, we're going to jump straight to the integral test, and here's what we will do. We'll say we can go from 1 to infinity. Say this is x all over e to the x. And immediately, I'm going to say limit as t goes to infinity. You definitely want to get into that habit. And guys, for the sake of time, I hope you can see that I decided to raise e to the negative x up because now I hope when you look at that integral, you're thinking, wait a minute, what looked to be kind of bad before to break down, we just recently, last chapter, spent time on how to do something like this. How would you integrate that? What's the quick way? Tabular. Let's see, let u equal x, let dv equal e to the negative x. Derivative of x is 1, then 0. Antiderivatives, you have to reverse the chain rule. You'll divide by a negative 1 as you do that. Take derivatives to work backwards, upwards to make sure that you're fine. But this would be a plus, then this would be a minus. So yeah, tabular's coming back for some of these problems. Wow, that's kind of neat. So I've got this limit as t goes to infinity. And then we'll have, for our first grouping, negative x e to the negative x. Then I'm going to say minus e to the negative x. But I'm going to work that out between t and 1. And the big question is, can we figure out what's going on here? Well, real fast, we can take the limit as t goes to infinity of negative t. By the way, I'm going to bring this down